Okay, welcome back. Now, a couple of remarks. One question that may come up is, hey, why do we need to use inverse matrices when we have Gauss's method? And there's really two reasons. One is if we do the work and we find the inverse matrix for a linear system, then what we have is we can use that same matrix to solve other related systems. For example, if we keep the coefficient matrix the same, but we start messing around and changing the constants, then we have a related system, and we can use the same the inverse matrix to solve very quickly. Okay, so for example, instead of 3 and 2, if I just change the constants to 5 and 1, well, now that we've already solved and we've got our inverse, we already know how to get the identity matrix here, which is going to be our matrix of 1/3, 1/3, negative 1/3, and 2/3. Okay. Or no, sorry, I got this backwards. U is this. Okay, and so now all I have to do is I can now solve this easily by setting up the our inverse method. So what do? We have xy is equal to 1/3, 1/3, 2/3, negative 1/3 times what? Times our constants, right? Just like we saw before. Okay, so now we set up our inverse set up the inverse equation, well, using the inverse method. And so if we do this, or actually, hold on. Yeah, that's right. That's right. Yeah, because if we multiply on both sides, yeah, we'll get xy, yeah, I had it right, equals, because this will give us the identity, right? So this goes away, and then we'll get xy times, yeah, 1/3, 1/3, 2/3, negative 1/3. Maybe I haven't had my coffee. Oh, and then of course, 1/3. Okay. So that's one advantage. So now the other advantage is that we can explore a system's sensitivity. Okay. So if we tweak the constants a little bit, what kind of effect is that going to have on the system? We can explore that too, if we know the inverse matrix. And we can do that very easily and quickly. For example, let's go back to the original system. So I have 1, 1, 1, negative 2 times, times xy equals 3, 2. Okay, so that's what we had before. Keep messing this up. There we go. Okay, so that was the original setup. Okay, so now what if I change this just slightly? If I change the constant by 100th of a point, what's it going to do to the system? And so again, if I think about this as multiplying by the inverse on both sides, so I'm going to multiply by the inverse, so that's going to be a third, 2/3, and negative a third, right? And I'm going to do the same thing over here, just so you guys see what I'm doing. So now I'm going to multiply over here by 1/3, 2/3, negative a third, and we have 3.01 and 2, right? So this here is just going to give me the identity. And so what I'm going to end up with is xy is equal to 1/3, 2/3, negative a third times 3.01, 2. So now what do I get? Well, I'm not going to, I'm going to leave it expanded, but what I'm going to get is this. I'm going to get 1/3 times 3.01 plus 1/3 times 2. And then I'm going to get what? 2/3 times 3.01 minus 1/3 times 2. Now let's look at this. So what is this telling us? So if we change by 100th of a point, right? We go from 3.00 to 3.01, then it shows that the first component of the solution changes by 1/3 of that change, right? While the second component moves by 2/3 of the change. So this is sensitivity analysis. This is what we look at when we look at sensitivity analysis, okay? This is kind of what we do when we're doing sensitivity analysis. Now, so we could use it to decide how accurately we must specify the data in a linear model to ensure that the solution has a desired accuracy. Okay, so that is an advantage.